My project title is Design and Simulation of Broadband Terahertz Metamaterial Absorber. First of all, I am going to start with the question, why terahertz? Because the electromagnetic region have 7 different waves like radio waves, microwaves, infrared waves, visible rays, X-rays and gamma rays. In this electromagnetic spectrum, I chosen a terahertz waves. This terahertz wave is placed in between the microwaves and infrared rays in the frequency range of 0.1 terahertz to 10 to the power 12 hertz. So terahertz means trillion cycles per second. 1 terahertz is equal to 10 to the power 12 hertz and it's 1 picosecond in time. Reason for choosing the terahertz region is it provides higher bandwidth and lower diffraction compared to microwaves and millimeter waves, and it provides the better line of sight communication, and it is used to transfer the large amount of data without any losses. And here copper is used as a perfect electric conductor. So because of this reason we choose the terahertz region. Also in the microwave region many devices already came like antennas, filters, absorbers. So microwave region is already engaged with lots of devices. So we are going to develop the filters, absorbers and antennas in the terahertz region. So in this project we particularly chosen a metamaterial absorbers in terahertz region. So the next one is metamaterial absorber. So the metamaterials are artificial materials because it provides the properties which are not readily available in nature. These materials usually gain their properties from the structure rather than composition. The design parameters include physical construction, material and geometry. Compared to the natural materials, these metamaterials provides the negative values of permittivity and permeability simultaneously, but it is not found in nature or discovered. Okay, so generally the metamaterial absorbers consist of 3 layers. These are typically metamaterial absorbers mean it's having only 3 layers like bottom layer and middle dielectric substrate layer and top resonator layer. The dielectric substrate layer is placed in between the top resonator and the bottom plane. The bottom and top is a metal layers. The metal used here is copper, and the in between dielectric substrate is placed. The substrate used here is polyimide or FR4 depending on the frequency of operation. The metamaterial absorber design, the top layer like first pattern layer is critical in metamaterial absorber design because it can be tuned to fulfill the impedance matching condition with the environment and achieving zero reflection at resonant frequencies. And the second dielectric layer is a spacer used to dissipate the electromagnetic wave, and this last final ground layer blocks all the incident electromagnetic waves. So metamaterial absorber. So in the name in the sense we need to calculate the absorption rate of the absorber. So in the absorption rate of the absorber calculated by using the formula A of omega equal to 1 minus R of omega minus T of omega. Here omega is the angular frequency, A is the absorption rate, R is the reflection and T is the transmission. Here the electromagnetic waves cannot pass through the bottom metallic plane because the bottom metallic plane copper blocked all the incident electromagnetic waves. So the S21 values like transmission value is automatically 0. So our aim is to make the reflection value as 0 by increasing the chance to get absorption value as 1. Next, why broadband metamaterial absorber? What is the importance of broadband? So the broadband metamaterial absorber used in civilian and military applications like photovoltaic cells, bolometric applications, photo detection, steel technology and mechanical manipulation. Also achieving broadband absorption especially in the terahertz region still remains a challenging task because of the intrinsically narrow bandwidth of surface plasmon polaritons or localized surface plasmon resonances. Next, we are going to discuss about the literature survey. So, the first paper is a polarization insensitive and omnidirectional broadband terahertz metamaterial absorber based on coplanar multi-square films. So, in the name, in the sense we identified, the author used multiple square films or coplanar method used to develop a metamaterial absorber, and the substrate they here used is silicon dioxide, and multi-square patches structure is formed in the top of the patch. And the next paper is a broadband terahertz absorber using multi-layer stacked bars. So here also, in the name, in the sense we identified, they are using multiple layers to achieve the absorption rate. Multiple layers increases the fabrication efficiency. So here they are stacking the 12 metallic bars. Actually, metamaterial absorber means 3 layers, but they are using the 12 metallic bars, and also they are using the gold as the metal. So it increases the cost also. And the third paper is wide angle broadband terahertz metamaterial absorber with a multi-layered heterostructure. So here also author used the multi-layer structure to develop the absorber, and the bandwidth here is 300 gigahertz, and the absorption rate is 98.6% average. And the fourth paper is composite structure based transparent ultra broadband metamaterial absorber with the multi applications. So here they are used the ITO metal, indium tin oxide is the metal layer, and the PET is the dielectric substrate. So it provides the optical transparency, because ITO with the PET provides the optical transparency, and they are using the multiple layers to achieve the absorption rate. And the fifth paper is a tunable ultra broadband metamaterial absorber with a multi-layer structure. So here also author chosen a multiple layers to achieve the absorption rate, and the achieved absorption rate between the frequency is 1.63 to 3.86 terahertz with 90%. And the last paper is broadband terahertz metamaterial absorber based on sectional asymmetric structures. So the absorber integrates 4 sectional resonators into a small cell, which means in the top of the patch resonator having 4 different types of cells. So the absorber is made of gold and Si3 and 4. The top layer is an array of sectional asymmetric AU resonators. So from the literature survey, we framed the objective. In the from the literature survey, the author mostly used multiple layers or multiple resonators in a single unit cell. Okay, multiple layers or multiple resonator in a single unit cell to achieve the higher absorption rate. But our objective is without using the stacked layers or multiple resonators in a single unit cell. Okay, so the total numerical simulation and design process is done by using CST Microwave Studio software, and we are going to take the simulated parameter like absorption rate, return loss, absorption rate in electric and magnetic modes, and polarization and incident angle plots, electric field distribution, magnetic field distribution plots, and surface current distribution plots. So problem statement from existed works. So already I told the authors mostly used multiple layers or multiple resonators to achieve the higher absorption rate. So that point is listed here. The first is combining multiple metamaterial structures with appropriate resonant frequencies into a large cell, and the second is nesting, which means multiple metamaterial structures or resonators in a single new cell, or third one is stacking. So different types of layers in arranged in a different multi-layer cell, and fourth is based on doping. So the proposed method without using multiple layers or multiple resonators in a single unit cell, we will give one or better metamaterial absorber with a higher absorption rate. So our aim is to design the absorber without using stacked layer or multiple resonators. So this is the workflow. First of all, we need to choose the substrate. So choosing a substrate is the challenging task. So here we will use the conductor as the copper, and the substrate is the polyimide. So and then choosing dimensions and set boundary conditions and frequency values. So next one is the design is simulated by using CST Microwave Studio software, and some of the output we will take from CST software, and the simulated output fulfill the expectation is so okay. So metals ITO and dielectric substrates SiO2. So generally copper is used as a conductor in most of the general cases, but here we are using the ITO. Indium tin oxide is the metal, because the indium tin oxide provides the higher bandwidth in the terahertz frequency region. Okay, in the terahertz frequency region, ITO is the best. So we are using the ITO as the metal, and dielectric substrate is SiO2. That SiO2 dielectric constant value is 11. And dielectric is calculated by using the formula epsilon r equal to n square minus k square, and tan delta equal to 2nk divided by n square minus k square. Here epsilon r is the relative dielectric constant, tan delta is the loss tangent value, and n and k is the real and imaginary part of the complex refractive index. And the software used here is CST Microwave Studio software. So this is the proposed metamaterial absorber design. First one is perspective view, and top view and the back view of the structure is shown here. So this is the unit cell profile of the proposed metamaterial absorber, which means the absorber is designed by using these parameters. So and the absorber having 3 layers, we already know. Here the ground width and length is 100 micrometer, and substrate is same 100 micrometer, and the radius of the circle is 65 micrometer. The middle substrate height is 50 micrometer. In this picture, the SiO2 is represented in yellow color and ITO is represented in pink color. So already we told metamaterial absorber having 3 layers. So bottom ground plane, dielectric substrate, and a top resonator. So this is the simulation output of the absorption rate curve. Here 1 represents the 100% absorption rate. This picture shows the absorption rate between a wavelength and absorption rate. So x-axis is the wavelength and y-axis is the absorption rate. So this is the graph drawn by using Origin software. We will save the text values from CST Microwave Studio software, and upload in the Excel format to Origin. So it will give a graph like this. So here ITO is the ground plane, SiO2 is the dielectric substrate, and the frequency, 2 different frequencies, 0.5726 and 1.1462 terahertz with a 99 and 99.7%. So and it is cover the broad frequency range from 0.511 to 1.169 with the corresponding bandwidth of 0.658 terahertz. So our resonant frequency is 0.57 and 1.14. Absorption rate is 99 and 99.7%, and bandwidth is 0.658. So this is the existed design. This work is done in phase 1. So in the phase 2, we are going to develop this design, because we need to increase the bandwidth still. So our design is little modified to get the better bandwidth value, because we are designing the broadband metamaterial absorber. So broadband means we need to cover the higher bandwidth range. So in this matter, we will develop the proposed metamaterial absorber. So this is the next level design. So the perspective view, front view, and back view of the absorber is shown here. So this is the design highlights. Here also we are using the ITO as the metal, but we chosen the material is PET. PET means polyethylene terephthalate, because in this ITO with the PET combination provides the optical transparency. Optical transparency means the light is free to move inside the structure, which means it is used in the solar cell applications, because in this PET structure absorb the electromagnetic waves from the electromagnetic spectrum, and it is used in the solar cell applications after converting these waves form into charge form. So this is the different developing stages of metamaterial absorber. So this is the shapes used to design the absorber. So the first one is used for the square shape and circular cone shape and cylindrical shape. Whatever we need, the shapes will help. So the next one is material properties. So here used the ITO as the metal and PET is the dielectric substrate. The epsilon value of the PET is 2.98, that is dielectric constant, and mu is 1, and tan delta, which means electric tangent, that value is 0.031. And initial condition settings, we need to develop the metametrial absorber in terahertz region. So the frequency we chosen is terahertz and dimension is micrometer, temperature is Kelvin and time is picosecond. And boundary conditions, so in the x and y minimum directions we are going to give the unit cell boundary condition for designing the metametrial absorber, and open add space condition is we need to give for z directions. And the next one is background properties. The background is always normal while designing the terahertz metametrial absorber, so we are choosing the normal as the material type. And the frequency range settings, our absorber is resonated between 0.3 to 1.4 terahertz, so we give the frequency range here. So this is the absorber, proposed absorber, developed absorber from the original structure. ITO is the metal, PET is the dielectric substrate, and the corresponding designed parameters with value is shown here, and PET is represented in blue color, ITO is represented in pink color. So this is the simulated output. This graph shows the absorption curve, which is between wavelength and absorption rate. X-axis is the wavelength and y-axis is the absorption rate. It is nearly achieved the 99% of absorption rate. So this is the developed graph from origin. So bandwidth here we achieved is 0.7 terahertz, and it's covered the frequency range from 0.3 to 1.4 terahertz. So this is the return loss curve. Here we achieved the return loss is minus 55 dB nearly. So if we achieve the below minus 10 dB means it will give the better, very good absorption rate. Here we achieved the minus 55 dB return loss. So it is used to get the near unity absorption. So the combined output is shown here from this table. Frequency is 0.45 into 1.18 with the corresponding absorption rate is 98 and 99.7, and the developed metametrial absorber gives the bandwidth is 0.7. So this is the simulated output. This picture shows the electric field distribution of the proposed absorber. The side, the color bar shows the intensity calculator. So because of this intensity calculator, we need to monitor a current which place is having the maximum electric field distribution. So red is maximum and next to maximum is yellow. So the inside of the patch structure having the maximum electric field distribution. So the overall patch structure also having the maximum electric field distribution, and the surface of the dielectric also having the maximum electric field distribution. Next one is magnetic field distribution. Here the magnetic field is maximum at the patch structure and the surface of the dielectric fully at the frequency of 0.45 and 1.18 terahertz. From the intensity calculator, we find the magnetic field distribution places. And the last one is surface current distribution. So we got the maximum yellow and green color. So the yellow and green is occupies the fully occupies the batch structure and the surface of the dielectric. So we got the better surface current distribution inside the metametrial absorber structure. So this is the plot showing the different polarization angle pi, which means if we need to tilt our metametrial absorber in the free space means like 0 degree, 30 degree, 15 degree, 45, 60, whatever the degree, we need to get a same absorption rate while changing the angle values. So that is the better absorber. So in our case, actually some absorption and frequency of the structure will changing the pi values because of the asymmetric nature of the structure. Because it provides the because of the structure asymmetric, it gives the little variations in the graph. So it is shown in this figure. And the same while changing the theta values, theta is the incident angle, pi is the polarization angle. So by changing the theta incident angle, we got the graph like this here. So here also the angle is, while changing the angle values, we got the little deviation from the original graph value. So it is polarization dependent in nature, and polarization and angle dependent in nature. So this is the overall simulation output inferences. So the proposed absorber having only 3 layers without using stacked layers and multiple resonators in a single unit cell, and it covers the 0.3 to 1.4 terahertz, and the ITO act as a ground plane as the circle with a 4 cross sector pattern in radiating patch. The first designed absorber designed by using SiO2 structure and bandwidth achieved here is 0.658 terahertz, and the proposed design, the next design, we used the PET as the dielectric substrate because of achieving the optical transparency, and the and the bandwidth achieved here is 0.7 terahertz, and the simulated output is drawn by using Origin Pro software. So this is the conclusion. The importance of broadband metamaterial absorber and the terahertz region is explained, and introduction about absorption rate and the reviews about broadband metamaterial absorber is explained. Here the metamaterial absorber is designed and simulated by using terahertz frequencies. Electric field, magnetic field and surface current distribution plots are analyzed. So the studies about polarization and angle independent mechanism is analyzed. So the target work is broadband mechanism will be analyzed in different types of substrate, because we analyzed for SiO2 and PET electric substrate, and next we are going to design the metamaterial absorber for different types of substrates with different types of metal values. So these are all the references. Thank you.